Yo, yo, what is good?
YouTube.
Today, I'm going to do something AI related, stable diffusion. People have been talking about this, on all forms of social media. People are now questioning, like, what even is art, right? So we can look at AI and see it as an adversary or an ally. I would like to kind of talk more about AI and maybe how it kind of plays a role in my life and your life as well. And furthermore, I would like to explore what I can do with AI in my music, my art. And I think right now we're in a very exciting time. And with that comes controversy. So, what a lot of people get wrong is that they think that AI is like alive and it's the thing that's conscious and making decisions about the subject matter and the details. And that's just a misguided way of looking at it. And we'll get into that more. And hopefully, I can explain how these things work in a way that makes sense to everybody. Right now, what we're looking at is the website Hugging Face, and they're putting out some resources that actually you can use to use Stable. Now, there's a couple different ways you can interact with the API, the pipeline, however you want to put it. This website or this portal specifically is an image variation generator. So what you can do is upload your own image. So I found this image in a bookstore and I thought, what if we could turn this into a really like high detail render? What we can do is throw that into this image variation software and have it work on that. So this has been running for like the whole day and I don't even know if it's going to be finished by the morning. And in the meantime though, what we can play with is Google Colab. So what we're looking at here is the Colab page for Stable Diffusion. So look up Stable Diffusion with diffusers if you want to play with this yourself. Follow along. I would highly recommend it as it's not that complicated to mess around with. What you do need to do, however, is set up an account with Hugging Face, and that'll allow you to actually use this. There's a cell that I already satisfied that requires it. So I have an account and I used it. So let's talk about it. Stable Diffusion is a text-to-image latent diffusion model created by researchers and engineers from CompViz, Stability AI, and Leon. It's trained on 512 by 512 images from a subset of the Leon 5B database. So what they're talking about here is text-to-image latent diffusion model. Let's break that down. Let's start from the very back, okay? Model. So when we talk about AI, and this is, keep in mind, Stable Diffusion is a fairly advanced concept in the field of AI. So, like, if this is going over your head, or if you have questions, like, don't worry, I'm gonna get you there. So models are the generic way of referring to a network that has been trained essentially, and that's a very basic way of looking at it. So after you run your training process and the algorithm has learned something from that data, you now have what's called a model. So that model has a certain attributes that determine its performance in many different ways, including accuracy when making predictions or the ability to create a convincing image. So model is a very broad term used in the field of AI to refer to a trained algorithm. And diffusion is referring to the type of model. So we're not just using a regular dense network, right? So like that would look like this, where you have all the nodes connected. These are the neurons and these are the layers. So this might be a better place to start, but just real briefly, we'll talk about this. Each row or each column of neurons that you see here is referred to as a hidden layer, right? So this is kind of what gives it its complexity and ability to learn different patterns and structures, right? So we have certain inputs that connect to these nodes, which crunch the data in a specific way that allows us to make predictions. That's the very most basic core of like what's going on in these networks. So when we're talking about stable diffusion, we're not just talking about any old network. Like we're talking about a network with very many layers. We'll just say that diffusion is the specific machine learning approach towards this kind of technique for generating images. So when they say like latent diffusion model, so latent is referring to how they take that data and kind of condense it in a way that not only makes it easier for the computer to understand and process, reduces the size, dimensionality, all that good stuff. One way you could think of it is turning data into like a vector, a matrix, that kind of thing we can use to actually operate on and do interesting things with. Now, text to image is a generic way of referring to any AI or any kind of technology, technically, that takes text and produces an image. In our case, again, there's a way of encoding these texts into latent like vectors that we're going to talk about later. So, moving on, this model uses a frozen clip VIT-L14, a text encoder, to condition the model on text prompts. With its 860M UNet and 123M text encoder, the model is relatively lightweight and runs on a GPU with at least 10 gigabytes of VRAM. The Colab notebook shows how to use Stable Diffusion with the Hugging Face diffusers library. Okay, so all of these like fancy like abbreviations are just referring to either different companies or like databases that they've created. This frozen clip in text encoder is actually key because this is the technology that they're using to encode the text, which can make a big difference. All right, let's get started. So how do we use this pipeline? Before diving into this and how it functions, let's try it out. In this section, we show how you can run text image inference in just a few lines of code. What we need is to use a GPU runtime, and it'll inference much faster. So we'll just run this prompt, NVIDIA SMI. And then what next we can do is install diffusers, SciPy, FT5 transformers, all of which are available to us here in this cell. So once you have that installed, might take a minute. You need to accept the model license when that's done, right? So we can go run this one. I guess we need to explicitly tell Google Colab that we want to run widgets. And we can log in with our token. And I'm in. Awesome. Let's get started now. And now we can actually start generating prompts, right? So what I did here was I generated some prompts earlier just to get us started. The one that they have default is pretty cool too. You'll probably see it if you are following along. The astronaut riding a horse. So what we have here is a cubist painting of DNA replicating. So of course it's very abstract and peculiar looking, but I can kind of see it. I think that this wasn't the best like text example, but I thought this looked very like cool. Like it looked like it belonged to a Picasso collection or something. So we already see like the AI is pretty good at stylizing in different fields of art, such as like painting, stuff like that. I also asked it to generate a subterranean lab. So this is sort of photorealistic looking. Some other things, I watched the Woodstock documentary and I just decided Summer of Love at Woodstock. It's kind of, I don't know, the people are kind of creepy, but it does look like an actual photo in a way. Like they got the same like I guess like saturation and all that. I don't think that the model is the best for generating like human structures and stuff like that, but still an interesting result nonetheless. Another one I tried was a photograph of an underground techno rave with lasers and an LED wall, and this is what it gave me then. If someone showed me this picture, I would have just think it was a show that they went to, but there is something sort of like surreal about it, and we'll talk more about that. But in the meantime, I thought this one was fucking hilarious, dude. I typed in Archangel Michael throwing a Kamehameha wave at a demon, and it literally just depicted Goku and I think Vegeta like duking it out in heaven as like a biblical painting. Let's start generating some prompts. So this prompt, let's change it to something else. So like, just so you know, there's a few sort of like illegal words, but if I type in a painting of glitch art, Potential NSFW content was detected in one or more images. A black image will be returned instead. Try again with a different prompt. And I just don't understand that because there's nothing not safe for work about glitch art. But I suppose that the safety module included has some peculiarities that haven't been worked out yet. That's fine. We'll just go and choose a different prompt. A crayon drawing of the Mona Lisa. Maybe that'll be cool. Okay. Interesting, but let's try a crayon drawing of like something, some kind of famous landmark, like I don't know, Mount Rushmore. Let's say like a children's crayon drawing. Okay, there you go. I like it. Definitely looks like a crayon drawing of something. I could see a little kid paint or drawing this and being like, "It's Mount Rushmore." Let's try one more in this cell before moving on. Let's say a self-portrait of Dali in the style of surrealism. Maybe that will be cool. Interesting. Okay, so we've seen a variety of results so far. Some enthusiastically pleasing and some rather not. This one is somewhat unsettling and at the same time pretty good looking too. Alright, let's see what happens when we do this. So what we can do here is if we want a deterministic output, we can pass a random seed to the pipeline. And every time we use that same seed, we'll have the same image result. So like, okay, in this case, check it out. Like, actually I like this one, but just burn this image into your mind for a second. Alright, we're going to change the random seed to 102. And then back to 1024 after we see this. So if we generate with a different random seed, we should get a different output. Wow. Okay. And now we're going to try again with 1024 as our seed. And as you can see, it's the same result as we got last time. Again, I'll try 102 just to verify this concept and show that it's not pure chance. So this random seed essentially determines the state of the noise that's used in the Stable Diffusion process. And that's something key that I'll talk about more later. And we can talk about randomness and all that good stuff too. So you can change the number of inference steps, and this generally results in like better output. So, let's try with our favorite seed 10 or 102 with inference steps of 50 as they recommend. And then once that's done, we'll bump it up to maybe something more, like 250. Okay, so, it looks pretty similar. I don't really see a difference between these two. So now let's try like 250 inference steps. And then that might take a minute, so let's come back to it. The guidance scale is a way to increase the adherence to the conditional signal, which is, the text in this case, as well as the overall sample quality. So what that means is if we give it a higher rating, then it'll actually resemble more the original image or the text that is embedded into the data. Sorry, this one's almost done, so let's talk about this. Not that different, honestly. I mean, I was expecting more of a difference. Let's try something like dramatically small. Let's try something like 4 steps. Whoa. Interesting. So yeah, like I think after it reaches a certain number of steps, it kind of converges. 3. I'm kind of curious to see the difference between 4 and 3. Oh, interesting. So 3 iterations is not safe for work. So I guess we're going to stick with something above that. So yeah, now we start to see something that kind of resembles the last cell a little bit. I'm just gonna do this. I'm gonna add some code and just copy and paste it just to show how it progresses. What the fuck? That is let's try. Actually, okay. This is what I should have done. I'm gonna add another text code here. Copy paste, and then we're gonna give it a seed of 1024. That way we can kind of compare it to this one here. So let's try a text prompt here that we want of a, you know, like a sort of collage of sorts. We can say Transformers evolving into creatures. Okay. So yeah, this is gonna be a lot of the same thing moving on from here. Just sort of like giving you different approaches if you want to create multiple or different sizes. Let's see, let's see. Ooh, okay. Okay. I mean, it's interesting though. Like, I personally think that this is like a stylized rendition of what I typed in. This one looks like almost photorealistic version, but it's not quite there. This one, I don't know about this one. This one's kind of abstract, I guess, but still has an element of photorealism, which I like. So, pretty interesting run there. Let's try one more with this kind of like grid cell. So let's say casting caustic rays in an industrial lab. So yeah, this one might take a minute, so we'll come back to it. But let's just talk a little bit about what's going on moving forward. So, okay, because the model is trained off of images that are 512 by 512, it's very easy to override this, but basically, if you aren't considerate of that, then you might not get the best results. So, going below 512 might result in lower quality. And then going over 512 in either direction will repeat image areas, so the global coherence will be lost. And then they say the best way to create non-square images is to use 512 in one dimension, as we can see in the height, and a value larger than that in the other one. So like, let's say we switch these two. Let's say a Polaroid photo of like something from the future or something like that, like of the year 2077. Interesting results. Okay, so this one just like straight up looks like a lab of some kind. This one sort of liminal. This one's a lot like the prompt, actually. This one right here, because you have like the lab, but you also are casting rays. I like this one a lot for some reason. Just looks like vintage. This one's also interesting, but kind of weird. Like, I asked for platonic solids, but they're giving me like Dungeons and Dragons die. I don't know. And I don't know, this one looks pretty sick. Yeah, like these are pretty cool. There's just something off about some of them, but some of them look very convincing to me, like this one. And this one looks more like a piece of art. So, nonetheless, you have to experiment to kind of get what results you're looking after. So, generating non-square images. A Polaroid photo of the year 2077. Whoa. See, like, because Polaroids are already kind of lo-fi, like, it makes it easier, I think, to trick the eye, but this, like, is only unsettling because I know it's fake, but these people don't exist, really. Like, they exist in the latent space of, like, the Stable Diffusion's model, but, like, these are people who don't exist. This photograph doesn't exist, and there's just something so odd about that. I don't know. It's like the image itself like triggers all of the, you know, like anything you would feel like from looking at a picture of a human, but it's just, you know that these don't exist. So again, very strange, very strange. Now, let's talk about the theoretical part. So they outline it here. They say it's based on a particular type of diffusion model called latent diffusion. And you can read about it here if you're a nerd like me, alright? You don't have to, but this is, if you're a big boy, then you would. But we can still have fun with it and learn about it just by sticking with this Colab page, alright? So general diffusion models, they're machine learning systems that are trained to denoise random Gaussian noise step by step. So it just has an iterative process that organizes patterns of noise into something more orderly, I'm assuming. And then that helps us get a sample of interest, such as an image. So we're basically reorganizing pixels, starting with noise, into something that resembles something that we like, or that we want to see, or have prompted. For a more detailed overview of how they work, check out this collab. So this collab, I was checking it out. This is all about diffusion in a more broad sense. So it kind of shows you how you start with a noise and can organize that noise into something that resembles an image. Alright, so that's just a little bit more advanced, and maybe we'll talk about that next time. But I want to keep this stable. I want to wrap this stable diffusion session up soon, so I can move on to the next thing I want to share with you guys, which is some Max for Live projects I started with Stable Diffusion. So diffusion models have shown to achieve state-of-the-art results for generating image data. So basically it's fire. But one downside of diffusion models is that the reverse denoising process is slow. So that process we just talked about, denoising, is fucking slow as shit. So in addition, these models consume a lot of memory because they operate in pixel space. And if you don't know, pixels are like images, like if we're just talking about standard definition, like 1920 by 1080, that's a fuck ton of pixels. If you want to go back to you know, like elementary math, basically, like let's talk about area. So like if we look at a square and we want to calculate the area, we know that all we have to do is to calculate the height times the width. And with images, it's the exact same way with the resolution. It's just a square, and each pixel represents a unit of area. So 1920 by 1080 pixels is already quite a lot. To achieve like standard definition, the amount of data that that image holds is like actually fucking huge. Okay, just to give you an idea. And that's why they generally would try to go for smaller images like 512 by 512. Even 512 by 512 is still a fucking lot. Like multiply 512 by 512 and you'll see what I mean. So they consume a lot of memory because they're in pixel space, and that becomes unreasonably expensive computationally when generating high resolution images, which is true. So therefore it is challenging to train these models and to use them for inference. Latent diffusion can reduce the memory, so this is solving the problem in compute complexity by applying that process over a lower dimensional latent space instead of using the actual pixel space. And that's the key difference. It's taking all the pixels and condensing them into data, almost like you would say like a zip file or a JPEG or any other like compression, like MP3. So that's the key difference between standard diffusion and latent diffusion. Is latent diffusion, they train with compressed representations of the images, like I just said. All right, and there are three main components, and that's the autoencoder, a UNet, which I don't know as much about right now, and a text encoder, which is the clip text encoder we mentioned earlier. Okay, let's talk about autoencoders. The autoencoder has two parts, an encoder and a decoder. In this case, the VAE model. The encoder is used to convert the image into that low dimensional latent representation, right? So it's just a way of spitting data into something that compresses it. And that will serve as the input in the UNet model. And the decoder transforms that latent representation back into an image. So what we're going to do is give an image or text or something, convert it into that latent space, process it in that latent space for all of its perks and benefits, and then decode it back into something that makes sense to us. And then what we're going to see is that during the training, the encoder is used to get the latent representation for the forward diffusion process, which applies more and more at each step. During inference, the denoise latents generated by the reverse diffusion process are converted back into images using the decoder. As you'll see during inference, we only need the decoder. The UNet, let's talk about that now. So the UNet has an encoder part and a decoder part, both comprised of ResNet blocks. The encoder compresses an image representation into a lower resolution image representation, and the decoder decodes the low resolution image representation back to the original high resolution image representation that is supposedly less noisy. Well, more specifically, the UNet output predicts the noise residual, which can be used to compute the predicted denoised image representation. Right? So like it's a way of interpreting like what direction or like how are we manipulating pixels in a meaningful way. Mathematically calculating like what do we need to do to these pixels in order to bring it closer to this image. So to prevent the UNet from losing important information while downsampling, shortcut connections are usually added between the downsampling ResNet of the encoder to the upsampling ResNet of the decoder. Additionally, the Stable Diffusion UNet is able to condition its output on text embeddings via cross-attention layers. So that's another one, cross-attention layers, which I'm not going to speak too much on because I don't know that much about yet, but you can kind of understand what it means when it says cross-attention layers. I imagine it's something that has to do with basically these shortcut connections between the downsampling ResNets and the upsampling ResNets. The cross-attention layers are added to both the encoder and decoder, part of the UNet, usually between ResNet blocks. All right, so that's probably the most confusing part of this whole thing is the UNet. That is sort of the meat and potatoes of this whole thing. And then the text encoder is the third part of this. It transforms the input prompt into something else. So it usually is a sample transformer-based encoder that maps a sequence of input tokens, which just means letters and words, to a sequence of latent text embedded. Inspired by ImageN. Why is it fast and efficient? Well, since the UNet of latent diffusion models operates on a low-dimensional space, it greatly reduces the memory and compute requirements compared to the pixel-space diffusion models. Alright, so this is where I'm going to start to lose everybody, and I've probably already lost everybody as it is. So let's just stop there for now. Understanding what we know now is that this is a magic piece of technology. Well, it's not really magic, but it's very good at what it does, and it's not perfect, but nothing ever is, and we're getting closer to more and more accurate results every day with these models. So Stable Diffusion is very fucking cool right now.